Welcome. In this video, I'm going to go do an exercise on electric submersible pump. So the goal of the exercise is we want to verify that the ASP model selected for the application will work properly for 5 times of the production profile. This field needs, this case, the wells need the artificial lift to deliver that rate that has been planned, and then we want to make sure that the pump will operate properly. We're going to do that with a flow equilibrium calculation, and then we're going to verify that the points of head versus Q fall inside the operational envelope of the pump. That means within the minimum and maximum frequency and the upthrust and downthrust lines. We're going to estimate ESP frequency and hydraulic efficiency for all years. And then we are going to compute required pumping power. The motor that I have selected, the capacity of the motor, I have to make sure that it's enough to pump what I am planned to pump. The study case we're going to use is the Peregrino field, which is offshore Brazil. And all the data is taken from this paper, which was published by Statoil, at that time now Equinor, and Baker Hughes in 2015. So let's go a bit through the paper. You see here you have where the field is located, which block, and it's not, I think it's not far away travel distance from Rio. The field consists on 2 platforms that where you have your wells. These are dry Christmas tree wells and such, and here you have the rig that you can use to pull in case there are failures of the ESP. You can use to pull the tubing out and replace the ESP. And then all the processing, most of the processing and storage is, I think, is made on this tank. So here I think you have just the Christmas trees and some manifolds. So they have categorized the wells into 3 types. They have high rate, medium rate, and low rate, and these are the profiles. We're going to be looking at the medium profile flow rate, minimum flow rate producer wells, and that's the profile. You see oil. Initially, there is no water being produced, but initially it's only oil. And then at some point in year 2, you see that the water production starts to increase and the oil production starts also to decrease. So we're going to look only before water breaks in. This is a reservoir that has an aquifer, and you are injecting the water that you produce on that aquifer. So we're going to be looking at those, and we're going to see at 5 points in time, or 5 this is all the different models that are being selected, they're being considered for the application, and this is one stage, I think. And there you have the rate through the stage, and there you have the performance. You have some that provide higher delta P, and they are high capacity for high rate, but some of them are smaller. These are all the ones that are considered. And here you see the operational map of all of these stages, of all of these models. Let's see the layout of the well, how it looks like. That's all the way at the end. So that's you have the formation, a horizontal well, then you have the flow until the suction of the pump, and then from there, which is in a kind of a deviated segment of the wellbore, and then you have like the vertical part, and then you reach the wellhead. Okay, so you have a bottom packer, and then you have the ESP below that, and then the fluid will enter through the ESP, and then it will through the tubing and then flow up. So and we have, so all the data we have in this Excel sheet. So you see this is the production profile that is for a medium producer. You have the rate of oil, the rate of liquid, and the rate of water, and you have reservoir pressure, how it is declining with time. This is something I have speculated on because this data I think was not provided there. We have some water injection from the platform, but I don't think we reach full pressure maintenance, so there should be some drop of pressure during the time. That's not so important. So this is a value, this linear behavior is something I have assumed. Yep. So if you see here, this is the curve for this medium producer. This is one stage, delta H versus Q. And these are the collection of points I took from the paper, and then I have fit that to a polynomial, order 4, which was the most accurate. And this is the efficiency, hydraulic efficiency curve with rate. That these are all the points, and these are all what I have used an equation of a 4th order polynomial also to fit it. Okay, so these are the equations that we will be using. You see here it's the performance plot with water. We have the pump that we are using here has here you see it's where all the calculations are made for of the map for water. So you see you have the coefficients for the head curve and you have the coefficients for the efficiency curve are the same that I showed before. The reference frequency, which is 60, and the best efficiency point is located at 2300 cubic meter per day. And you see here for different, what happens with frequency when you change the frequency. So say when you change the frequency from 30, you see 40, 50, and 60, is scaled up using that similarity law principle. And then you have the minimum um, uh, flow line, a maximum flow line, which is for up thrust, and the minimum flow line, which is for down thrust. And you have this best efficiency line, which joins all the points at which I have the best efficiency. Now, if we look at the plot of efficiency here, the head is plotted to the left and the efficiency is plotted to the right, and the rate is in the x-axis. So you see that for 30 hertz, that's where you have the maximum efficiency point, the rate. So that should coincide with this point here on the best efficiency line. But then when you increase the frequency to 40, so then you see that now the best efficiency point is here, and now the curve of the efficiency is shifted to the right. The value doesn't change, but it's simply shifted to the right. And then when you go to 50, so then this is the best efficiency point, and that coincides with this maximum point on the curve. And finally 60 hertz, then you see that this is the best efficiency point, and that coincides with that point there. So the efficiency curve, the values on x are not changed, but the values on y, they are changed due to the change in the frequency. Then furthermore, you see you have the correction with viscosity that's done in this, not on this chart, on this chart. Okay, you have the same coefficients of the head curve that we were that are for water, and then I have it's programmed here in this sheet the procedure from the Hydraulic Institute to correct the curves for viscosity. So let's take a look at how it looks like. So here the water, they are the solid lines, and then the dotted lines is the viscous oil. And this fluid that this field is producing is actually quite a viscous crude, and I have set here 100 centipoise. You see here 100 centipoise and the density 835. So that causes the following change to the performance map. Here you see first that the head it's reduced considerably. Okay, also you see for 30 hertz how the head is reduced, and then you see also the lines of maximum and minimum rate, they are also changed slightly, and also the best efficiency point. Let's look at the efficiency now, the efficiency curve. So here you have again the same thing, the solid lines, they are the water curve. So here you have the head to the left, and also the head here, this violet one to the left, with viscosity 100 centipoise, and then just with water, this is a solid line. And then you have the efficiency curve. This is the efficiency only for 60 hertz. So you have here for 60 hertz, this is for water, and this is for 60 hertz, but now for viscous oil. You see how not only it kind of is reduced dramatically, the values of efficiency due to be pumping highly viscous crude, and then also you see here for 30 hertz, the efficiency also is reduced dramatically with viscosity. Okay, so and here let's move a bit to the left. So here you have the data. We are going to be checking only these 5 years. So it's around 1 year, around maybe 1 year and 3 months, around 1 year and 9 months, and then almost 2 years. So here you have the rate of oil. As I mentioned before, no water is produced now from this field, and you have the rate of oil in standard cubic meter per day, and you have the reservoir pressure for all of these points. So this is what I have copied to this main sheet where we're going to make our calculations here. You see here some data. That's initial reservoir pressure. That's the J of the formation of all the flow, of all the horizontal section. Here you have the H1, which is the height that I have from the bottom hole all the way to the suction of the pump. So that will be the height difference between here and here. And I have also the length that is 380 meters. Here we're assuming vertical well just to make our calculations simpler, but I could also have taken into account the change the change due to the deviation of the wellbore. So here you have the h and you have the diameter of that section, 0.24 meters, and then you have the h2, which goes from the discharge all the way to the wellhead, and that is this other h you have here, and you have the diameter of that section, which is 0.14 meters. The wellbore radius is inclination with respect to the horizontal. It's 90. The roughness of the tubing and the casing is 1 to the minus 5, and you have 78 stages of the pump. And here you have the viscosity of the oil, which is 100 centipoise. This is at suction conditions. We're not going to assume that viscosity is changing with pressure and temperature. We're going to assume a single value. And you're going to assume also a fixed density of the oil, which is 835. Don't pay attention to this part. This is if you have water, and then you have to calculate mixture density, but also water. The mixture of oil and water exhibit emulsion behavior. So then the viscosity might be higher than that of the water or the oil alone. But for that, for this exercise, we're going to neglect this part. The bubble point pressure of the crude is 29. So we want to make sure that the suction pressure is always above 29, just to be sure to avoid gas liberation the suction of the ESP. So here we have reservoir pressure, water cut, and then Q liquid. And then let's calculate now the Q oil. That will be simply the Q liquid times 1 minus the water cut. Okay, so it's exactly the same because I have no water. The Q of water will be the Q of liquid minus the Q oil. Now let's calculate, we're going to move now to make flow equilibrium. So we're going to move from the bottom hole. We have it someplace here. We're going to assume it's at the heel. Okay, then we're going to move from here all the way to the suction of the pump. So first we're going to, we have the rate, and then we want to calculate what pressure do I need to apply here to get that rate. So as a bottom hole pressure, that I do with the IPR. So I believe I have an equation, PWF, that is giving me the pressure. This is simply a linear equation. Then I provide the total. This J is made for total liquid flow, so I should put the total liquid flow. The Q liquid at standard conditions, the J, and I block that J, and the reservoir pressure. And the only one I'm blocking is the J. The J will remain constant with time, but the PR and the Q will change in time. So you see here I found that I have to have 91, year 0.95, 0.98, 114, and so forth. Let's see if it did it properly. Okay. Now I need to move from the bottom hole all the way to the suction of the pump. And for that I have to make a calculation of pressure drop in the pipe. That calculation should be made with the local rate, and actually I should make it some sort of an integration because the pressure will be changing and the properties of the fluid are going to be changing. But I'm going to assume simply that the properties remain constant, density and viscosity of the oil, and I need to find the local rate at those conditions. Okay, the local rate simply is QO at standard conditions times the BO. And to find the BO at the bottom hole, then I'm going to use this table, PVT table. Okay, so you see here how it behaves, the P versus the BO. So initially you have an undersaturated part all the way almost to 29.4. Okay, and then it starts to have gas liberation, and then it starts to change strength and go down. Okay, so we're going to make an interpolation on that table to find out how much is the BO. But you see here all the flowing bottom hole pressures, they are above the bubble point pressure. So for that, we're going to use our function tab interpol that we have used before to interpolate linearly. And we say that the X is the pressure, bottom hole pressure. The column in which it is 1, 2, 3. And then the matrix is going to be the whole data set here. and that we have to block. So 1.16, 1.15 doesn't change that much. We don't have any water, so we don't have to be worried about that. We don't need to calculate local water, okay, but this typically is equal to very close to 1. So the Q of oil local at bottom hole pressure is going to be equal to this BO times QO. So you see that actually is higher than what you produce simply because you are liberating some gas. Yeah. Then the Q liquid will be simply Q water is going to be 0, and Q liquid is going to be simply Q oil at the bottom hole. Average density, this density is going to be simply the density of the oil, which we have here. We're going to assume constant density. Okay, and effective viscosity is going to be also the viscosity of the oil, which is this one here. In case we had water, then this density will, if we have some water, maybe the average density will be closer to the water, and that I have to do some calculation there. And also in case I have water, I might have here some emulsion behavior that I might want to take into account. But in this case, it's only oil, so I just use the density of the oil and the viscosity of the oil and constant. So now I want to calculate the suction pressure to the pump here, and for that I'm going to use a pressure loss equation, assuming that density, viscosity is the same, and the local rate remains constant, which we know is not exactly correct, but it's an approximation. So for that, we're going to use a function. You see here I went to the VBA module, I go to single phase hydraulic, and we have the IPR, a linear IPR that we have used. And we have a P in, so this function is going to give you the pressure required at the inlet of the pipe upstream if I provide the pressure at the outlet of the pipe. So that's not the one we want, because we are calculating co-current all the way from bottom hole to suction of the pump. So then we are going to use this one, P out. P out requires the Q in standard condition. This is in local. Okay, I should use here the local rate. The diameter of the pipe, density and viscosity, the length, the inclination angle, and the inlet pressure and the roughness of the pipe. Okay, simply making a calculation, calculating the friction factor, and then I have here, you see two terms. This is the P in minus the hydrostatic pressure drop minus the friction pressure drop. Okay, so it's very simple. I'm not doing any integration just to keep things simple, but I'm just calculating like assuming everything is constant. So that will be P out, P out. Here I have to provide, sorry, P out. And let's see what it requires. A Q, which is going to be this Q. Then the ID for that section is this guy here, and that I have to block. The density is going to be here. Viscosity is this cell here. Length is, we're assuming vertical section, so it's going to be this 380 that I have to block. Inclination angle of the wellbore, we're assuming that all the wellbore is vertical, so we're going to use 90. P in is going to be the flowing bottom hole pressure, this guy here, and the roughness is going to be this guy here. Okay, I block it also. So then if you see here, I have a 30 bar pressure drop from bottom hole to suction. Here I have again 30 maybe. Here again I have like a 30 bar, and here also I have maybe a 30 bar pressure drop. So I have, for all the points, I have a 30 bar approximately pressure drop between the bottom hole and the suction of the pump. Now I stop there, my flow equilibrium calculation, and I go from the wellhead all the way to the discharge of the pump. And that I have to calculate the pressure required by the pump to flow against wellhead pressure. And that wellhead pressure is connected to a separator, so it's equal to 7 bar. Okay, so for that I have to use the other function, which is here, P in. I calculate the pressure at the inlet of the pipe, providing the pressure at the outlet of the pipe. Here is an approximation because we might have remembered bubble point pressure of this oil is 29, so here it's 7. So in the top part of this tubing I will have gas liberation, and that will affect somewhat the pressure calculation. Okay, but I will do it simply assuming that it's single phase liquid and that the QO local doesn't change along this part of the tubing. But if I want to make it more realistic, I should include the pressure drop due to two-phase flow, okay, especially at the upper part of the tubing. Okay, so for that I calculate P in, and here I have to provide the Q, I have to provide the ID. In this case the ID will be the tubing ID, I block it, density, viscosity, length will be this length, I block it, inclination angle of the wellbore, vertical, P out, that P out will be the P at the wellhead, and the roughness is going to be this guy there. Okay, so it tells you that I required 173 bar at the discharge of the pump for this case. And here I require is essentially the same for all of them. Okay, 173, 171. So that tells you this is what you required at the exit of the pump, and this is what you have available at the suction of the pump. They are not the same, and this one is less than that one. That tells you that you need to have a pump. So what the pump needs to provide is the discharge minus the suction. Okay, so 113 bar and changing to 89, 73, 62, and 51. So it's reducing a bit with time. Okay, now we have the collection of points. We have the delta P, and then we have the liquid rate that we want to plot on our performance map. Okay, but let's make it in terms of head, because remember the performance map we typically make in terms of head. Okay, so it's this divided by density times 9.81. This is the definition of head, and I have to also convert from bar to pascals such that I am consistent with the units. It gives me meters. Okay, so these are the combination of delta H and also the combination of the rate. Okay, if you see now I have plotted now that here, and this is already having the correction for 100 centipoise and 835. So you see that the points actually fall very nicely inside the map. This is the initial time, and then it's going later in time. The rate is being reduced, and also the delta P is reduced. Okay, so that tells you that for year 1, or the first year or the first time, I need to apply a frequency close to 60. This one is a frequency between 45 and 60. This is a frequency close to 45, and so forth. Okay, but it seems that the pump is able to work. Okay, so that addresses the first question we had, that the points actually they fall on the envelope. Okay, but now let's try to estimate the frequency of those points. Okay. The way I'm going to do that, we're going to do a visual inspection. So we are going to change the frequency of this line to something higher, maybe to something to 59 here, very close to 60, until it passes exactly through that point. Okay, so the way we're going to do it, this one we change it to maybe 59. Okay, and you see now it's passing through that point, so we are going to assign that that frequency is 59. Okay, then we want to pass through the second point, which is something like 45, maybe 50, maybe 40, sorry, 45 plus 7.5, 52, 53. So let's try with 53. Okay, then we're moving that curve, the red curve is not yet there, so we have to go a bit lower. So let's try with 51. Okay, now it's passing more or less through that point. So let's say 51, that will be the frequency for the time 2. Then let's repeat for all of them. I will accelerate the process in this video, just that you don't have to see one by one. Okay, so we're not finished with all the points. So here you see the last one. that is around 37 Hertz. Okay, we cannot be very precise with visual inspection, but that's what we have. Okay, passing through the last point. So I find that I have actually to reduce during these times, 5 times I have to reduce the frequency from 59 to 37. Then we are done with that part. And now we want to read also the efficiency for those times. Because when we have the efficiency, then we can calculate the required pumping power with the equation that including the hydraulic efficiency and the mechanical efficiency and Q delta P. And then I can see if the pump that I selected, which has a motor of 760 horsepower, then it will be able to provide, it's enough for the application. So let's first put some points, some efficiency values. Okay, let's say 40% for all of them. Okay, and how to see how they are plotted. Okay, you see here he has for year the first time, second time, third time, fourth time. So now we have the frequencies for each one of the years. Okay, 59, 51, and we have to make sure that the frequency, so let's try for example for the first year, we want to see 59. You see the curve for 59 should be like that, very close to the curve for 60. Okay, but the point is down here because we have assumed a hydraulic efficiency of 40. But now it seems it's not 40, something higher. It should be someplace here, so maybe like 51 or 52. So let's change that to 52. 52. Okay, so see how it looks like. So now the point is very close. So let's try now with 51. Okay, you see now I'm very close. Now let's change the frequency to see the second point, which is 51. So I will change now the frequency to 51. Okay, now the efficiency curve is changing. It's now, this is the 451. Okay, now you see that the point that we have assumed 40 is actually shouldn't be 40, but should be something higher, maybe 48, 49. So let's try with 48. So it's actually, we were too pessimistic on the estimation of efficiency. Okay, you see it's almost very close. Let's try with 49. And now it's on the point. Let's do one more and then I will accelerate the video and so you don't have to look at how all the points are made. 46. Okay, so finally we completed the estimation of the efficiency, hydraulic efficiency. You see, it's also going down somewhat with time. And after I have now the hydraulic efficiency, I can calculate the power. The power, let's go to the equation that I'm using here for power. Is under the ESP calculation, and let's look at power. It should be someplace here. ESP power. Okay, so it's delta P across the pump. This is in bar times the Q at local conditions. And then I have the mechanical efficiency and the hydraulic efficiency, and then I have a conversion factor which converts from watt to horsepower. Okay, so then I have to use ESP power. That is requiring the delta P in bar. That will be this guy. The Q at the inlet of the pump, which is the Q of the liquid. Mechanical efficiency is very high. I block it, and hydraulic efficiency is this guy here. The hydraulic efficiency should be actually in fraction. Okay, so you see actually that it works very well, that design for almost all years except the first one, in which I need 800 horsepower and what I have is 760. So then that means that I have to use a slightly bigger motor to be able to provide for the time number one.